The most dangerous models aren't the ones that perform poorly. They're the ones that seem to perform brilliantly, but fail in production. This disconnect is almost always caused by methodological shortcuts, whether through deliberate manipulation or unintentional error. Today, I'll identify these critical errors, like data leakage and flawed validation, and provide a framework of disciplined practices to ensure the performance we achieve on paper is truly reliable in practice. All right, I know this slide says Introduction to Accuracy, and many of you are probably thinking you don't need an introduction. And you're right, we all know accuracy is a core metric. But the reason I'm starting here is to frame the central problem, not what accuracy is, but how we achieve it. As I'll demonstrate, the pursuit of a high score can tempt us toward shortcuts that artificially inflate performance, compromising the model's reliability and integrity. This is about ensuring our accuracy is earned, not just reported. Let's start with the key takeaway. Artificially inflating the reported accuracy of machine learning models is a serious concern in the field. This often happens because of shortcuts, usually due to methodological mistakes. Common issues like data leakage or improper handling of data can make a model appear much more accurate than it truly is. Ultimately, these practices undermine the reliability and generalizability of the models, meaning they would not perform well when applied to real-world situations. Let's take a moment to quickly summarize some of the most common shortcuts that can lead to artificially high accuracy during machine learning training. Data leakage, improper data splitting, inclusion of post-outcome features, overfitting, cherry-picking results, data snooping, misleading evaluation metrics, ignoring class imbalance, lack of external validation, use of diagnostic proxy features. Let's take a closer look at one of the most common issues, data leakage. Data leakage happens when information from the test set makes its way into the training process of a machine learning model. This introduces false relationships between the features and the outcomes, causing the model's accuracy to appear much higher than it actually is in real-world use. A typical example of this mistake is applying data manipulations, like pre-processing techniques, to the entire dataset before splitting it into training, validation, and test subsets. Doing so contaminates the data splits, leading to data leakage and unreliable evaluation metrics. Next, improper data splitting. This happens when we don't group data correctly. Then the model might end up memorizing specific cases rather than learning patterns that generalize well to new data. For instance, if we have several scans from the same patient, it's important to keep all of those scans together in the same subset, whether that's training, validation, or testing. We should never split scans from a single patient across multiple subsets. The main goal of data splitting is to see how well our model performs on data it hasn't seen before. If information from the same patient appears in both the training and test sets, the evaluation isn't valid. Since the test data isn't truly unseen, the model's already been exposed to that patient's unique features. Another important issue to watch out for is the inclusion of post-outcome features. These are features that are only available after the outcome has occurred, like treatment codes or discharge summaries. If we include this kind of information in our training, it gives the model access to data it wouldn't have at the time of prediction. This can make the model appear much more accurate than it really is, because it's using information that wouldn't be available in a real-world scenario. Think about it. If the diagnosis is already known, why would we need a machine learning model? The whole point of building these models is to help us diagnose or predict future outcomes, not to confirm something we already know. Next, overfitting. Very common issue. Overfitting happens when a machine learning model learns the training data too well, picking up on details that don't actually help it generalize to new data. This means the model may show very high accuracy, but it won't perform as well on new, unseen patients because it hasn't learned the underlying patterns. It's just memorized the specifics of the training examples. One key way we can spot overfitting is by looking at the training and validation accuracy curves during training. The relationship and trends between the training and validation curves reveal overfitting when the model performs significantly better on the training data than on the validation data as training progresses. Cherry picking in machine learning means only showing off the best results while ignoring the ones that aren't as impressive. This can happen intentionally to make a model look better than it really is, or even unintentionally due to our own biases. A common example is when someone trains a model several times and only reports the run where the model did unusually well, maybe because the test data was particularly easy, while ignoring the other, less successful runs. This gives a skewed impression of how well the model actually works. Cherry picking is a problem because it hides the true range of outcomes and can make us overestimate how effective a model really is. For real-world applications, this can be risky, since decisions might be based on results that aren't truly representative. Another term often used in ML training is data snooping. Data snooping is a broad term for any situation where information from outside the training data, often from the test set or future data, leaks into the model training process. This can happen through improper pre-processing, feature selection, or model tuning that uses information it shouldn't have access to. It leads to overly optimistic model performance estimates and poor generalization. When evaluating machine learning models, it's important to be cautious about relying only on aggregate metrics like accuracy alone. These metrics can be misleading, especially when dealing with imbalanced datasets. For example, if most patients in a dataset are negative, a model could simply predict everyone as negative and still achieve a high accuracy, like 95% in the confusion matrix shown on this slide. However, this would completely miss the positive cases, making the model useless in a clinical setting. So, while metrics like accuracy might look impressive, they can easily mask poor performance on minority classes and give a false sense of the model's true predictive power. Therefore, ignoring class imbalance is a big no-no. When one class dominates the dataset, the model often learns to predict that majority class very well, but fails to recognize the minority class. This can make overall accuracy look high, but in reality, the model is just biased towards the dominant class and missing important cases in the minority group. If you suspect class imbalance, it's important to look beyond just accuracy or the ROC curve. Always check the precision recall or PR curve as well. If the PR curve stays close to the baseline, that's a clear sign your model is struggling with the minority class and that class imbalance is a real issue. This visual cue can help you catch problems that aggregate metrics might hide. Relying only on internal validation results can give us a false sense of confidence about how well our model will perform. If we don't test on independent external datasets, we really can't know if the model will generalize to real-world situations. This can lead to overestimating its true predictive power, and the model might fail when actually deployed. Of course, sometimes it's difficult to access external datasets. In those cases, we have to make the most of the internal evaluation tools we have, like checking for signs of overfitting or class imbalance using our validation curves and metrics. If we don't see evidence of these issues, it's a good sign that even without external testing, our results are likely to be reliable. Another tool to check if a machine learning model is properly trained is to look at its performance on the training, validation, and test sets. During training, the model directly learns from the answers, so it usually performs best here. In validation, the model sometimes gets feedback to help tune its settings, so performance is typically a bit lower. On the test set, the model has never seen the answers, so this is the most realistic measure of how it will do on new, unseen data. Because the model has less and less access to the correct answers as we move from training to validation to test, we expect its performance to decrease at each step. If, instead, the model does better, for example, on the test set than on the validation set, this suggests something went wrong, like data leakage or improper splitting. In a well-designed experiment, performance should drop stepwise, from training to validation to test, reflecting the model's true ability to generalize. This is especially critical in high-stakes fields like healthcare. For instance, imagine you have two models, as in the graph on this slide. Model 1 initially claims a higher accuracy than Model 2. However, If Model 1 is badly trained, then its performance is likely to drop sharply when applied to new, unseen patients, and relying on its accuracy metric alone could lead to clinical harm. In contrast, Model 2, even with a slightly lower initial accuracy, would be the more reliable choice if it demonstrates good generalization. One last warning: using diagnostic proxy features. Using diagnostic or proxy features that are closely related to the target variable can result in misleadingly high model accuracy. The problem here is that these features might give the model information it wouldn't actually have in a real-world prediction scenario, which ends up skewing the results and undermining the model's actual usefulness. Think about it this way. We wouldn't need AI to make a diagnosis or prediction if we already had access to a feature that on its own gives away the answer. For example, let's say we're training a machine learning model to predict a patient's future weight based on certain life factors. If we include their current weight as one of those features, there's really no point in using machine learning. The answer is already right there. The model might look highly accurate during testing, but it wouldn't be useful in practice. So, it's important to make sure that the features we use in training are realistic and reflect what would actually be available in a real clinical or operational environment. It's essential to always verify and require comprehensive documentation from AI solution providers. This helps ensure they haven't inadvertently or intentionally relied on shortcuts, and it guarantees their solutions are valid, transparent, and truly applicable to your real-world needs. Main take-home message: remember, it's your patients who will ultimately be affected if something goes wrong. Even if a company claims FDA approval or says their research was peer-reviewed, how much trust are you willing to place in someone else having thoroughly checked for these shortcuts? At the end of the day, it's your patients and your own practice that will suffer the consequences if something is overlooked. To bring this presentation to a close, I'd like to share the perspective behind these insights. My name is Dr. Milan Toma. Professionally, my work is in applying machine learning to diagnose a wide variety of medical conditions. My students and I have published over 30 studies in this area, investigating everything from neurological diseases like Alzheimer's and Parkinson's, to orthopedic analysis of bone fractures and osteoarthritis, all the way to interpreting complex EEG and ECG signals. This research also forms the foundation for both a class I teach to our medical students at the New York Institute of Technology College of Osteopathic Medicine, and a book I've published, each titled AI-Assisted Medical Diagnostics. But while that is my background, the true wisdom I've shared today comes directly from my students. The lessons on avoiding shortcuts were forged while guiding them through these very challenges. My expertise is not my own. It is a direct reflection of their hard work and brilliant curiosity. Thank you so much for joining this session. If you'd like to connect or have any questions, you can reach me by email or find more resources on my website and social media. Also, if you're interested in diving deeper, be sure to check out my book. I especially recommend Chapter 3, where I go into detail about detecting the shortcuts we discussed today. Chapters 8 and 9 also offer lots of practical tips you can use right away. Thanks again, and I look forward to staying in touch.